Swayam Prabha. Digital India. Educated India.
In this class, we have a short video of the dynamic compaction process and how it is done in the field. You can see that it is being done next to a shopping complex. So, what you have seen is that it is a compaction using dynamic methods, where you try to compact as much as 10 meters of the in situ soil and improve its performance. As I just mentioned in my previous class, the way that we do is that we just have a tamper which will induce energy into the in situ soil, and this in situ soil becomes strengthened because of the energy impact that the material had. The energy whatever we have from the weight into the height, that is the potential energy, that gets transferred to the soil in the form of kinetic in the movement. Now, it gets transferred to this soil system. From that potential energy, it gets that whatever is the energy that gets transferred to the soil, and then there could be some energy losses here because the soil itself is a damping material. So, with the result that the soil is quite strong, but at the same time it may not have the full energy whatever is transferred, but the energy that is transmitted to the system is good enough to see that it performs as a very good material, wherein the settlements could be minimum and the bearing capacity is very good. So, as I said, this dynamic compaction is a ground improvement technique which can be very useful, which densifies the fills by using a drop weight. And as you saw just now, the drop weight is it can be a hardened steel plate, or even it can be a weight whatever circular or whatever. It is lifted by a crane and repeatedly dropped on the ground surface. The drop locations are typically located on a grid pattern, like we see that in a design now in a few minutes. the spacing of which is determined by the subsurface conditions and foundation loading and geometry. Essentially, we can have the most of the times a grid pattern, and the main thing is that the subsoil conditions, like the thing is that to what extent is that soil needs to be improved, and then what is the foundation loading that is coming, and the geometry, all that is very important. And normally, as treating granular soils and fields have always resulted in increased density, friction angles and stiffness. We will see this how it can happen. And as I just mentioned, this technique has been used to increase bearing capacity and decrease settlements and liquefaction potential for plant structures. In fact, this is one of the very important applications, and in shallow karst geologies where the soil has a tendency to collapse, it actually reduces the voids prior to construction, so that the sinkhole formation or potential is reduced. Then we also have been using this dynamic compaction for many of the landfill projects, because the landfills in the problem with landfills is that they have heterogeneous mixture of waste, like papers, food and debris, construction debris, and whatever you have waste materials. It is very difficult to construct or compact waste materials in a systematic way, but then the dynamic compaction has been quite useful. Why? Because it just directly gives lot of internal energy to the soil by means of this process of dynamic compaction, and the behavior or the properties of the municipal solid waste are not directly related to the anyway in the design. It just that it inputs lot of energy into the soil system, and directly it results in better performance of the structure. So, it has been used in parking lots, it has been used in highways, actually many places in years, particularly even in India it has been done, and to stabilize the large area of the embankment works. Then one of the most important considerations regarding the applicability of the dynamic compaction is the type of soil being densified. As I just mentioned, it is very good for granular materials, and granular materials, they enable excess pore pressures that develop during densification, they dissipate rapidly, in the sense that the dynamic compaction has been very much used with considerable effect in coarse grained soils, but then it has been quite effective as well in silts, clay silts and sandy silts, as well as in municipal solid waste, and so much so that it is one of the preferred options, particularly when the little, like faster, it should be the rate of or the you would like to need that area at a fast manner. Say for example, if you are trying for sand drains, it could take long time, but then in the case of dynamic compaction, it can be required, the area can be required quite fast. Like you must be able to design it properly, that is one thing, and then get the weights, get the tamping, get the proper contractor. Then once you have, actually the thing is in this process what you should do is that you will be compacting up to not less than 10 to 15 meters. You must be able to have the initial soil profile, say either using initial profile, soil profile, as well as a CPT profile or an SPT profile, and also after compaction you must be able to get the SPT profile or a CPT profile. We will see how they are useful to us in a minute, but the first important thing is that how do you go about design. The design is something that is very important in this process, but it is a very simple principle that, like you just compact a soil, then it has a shape, it has the weight densifies a system like this, a shape which can be a shape, the approximate shape of the area that is going to be densified could be in this form, and this is a sectional view, this is a top view of that, and this thing gives the, like you have a compaction here, you have compaction here, the spacing, the SG is a spacing, and A and B are the parameters. Say for example, B is the depth of area that you would like to depth of the soil that you would like to densify, and A is the diameter. Just we will see some of these parameters. Actually, but there is an approach available in literature which can be useful to find out actually in a design we know what is the depth to be improved. So, we should be able to know what is the number of blows required, what is the weight of the hammer required, what is the height of drop, what is the area of the cross section, in the sense that if you have a 5 by 5 meter 5 meter diameter. So, pi by 4 into d square will give you the area of impact, then B is the depth. So, there is some relationship available in literature which has been quite useful to come out with. Once you know this, you will be able to know the dimensions A and B, so that either with this knowledge you will be able to properly get the idea of what should be the in given that you have this weight, say for example 10 ton or 15 ton weight, and you know this is the height of drop and its area of cross section is known, you must be able to design what should be the spacing, what should be the spacing, and of course we should also cater to the depth of improvement also. So, we will see that in an example. For example, the required significant depth of densification is given by di is half into square root of W h into h. This is that a simple formula in which earlier also I showed in the previous class about on the dynamic compaction methods. The di is a significant depth of densification, Wh is the weight of hammer, h is the height of drop. Actually, in that previous design diagram that I gave, the depth of densification is nothing but the B. If you see the figures, they both are same, and if you know the hammer weight, the height of drop, the dimensions of the cross section, and thus the area and the depth can be obtained. Say for example, this is what we see, and this using this plot which is given in a Canadian Geotechnical Journal paper, you need to estimate the magnitude of this particular factor actually, and since these are all, you have some numbers here, say for example weight and height and all that, you have to you can determine the number of drops in a quite comfortable way, and you will also cross check what will be the A and D values, like what is the, so A is actually, A tells you the spacing and B tells you the depth. So, for example, in a typical example, weight of the hammer is about 18.5 tons or 185 kilonewtons, then the height of drop is about 26 meters, and the weight of the width of the hammer, say for example it is 5 meters. So, first step is you calculate this depth of significant influence. This is given by this expression. About 10 meters is what is required, about 11 meters now using these values, and now we assume D I have taken it as 5 meters and area of cross section is 25, I am just assuming it as square for a simplicity, and if you just get this B by D, actually when I have to refer to the graph where I should go by these numbers, I get a term called this B by D is like 10.96 divided by the diameter. So, 2.2 I will get from for this particular number, I get a number NH is equal to 220 kilonewton per meter square. Now, I know these weights already, say for example, I have given as WH as 18.5, height of drop and area of cross section, everything is known. So, what for corresponding to 220, I should just get back in this particular term the number of drops. So, for example, in this term I know what is 220. So, I am just getting back, working back what is the number of drops. So, you will get a number 14, and once you know this from the same figure, you can also get A by D. So, A by D in the same figure gives you 16 meters as a spacing. So, what it means is that thus using a square plate of about 5 meters for a height of drop of 26 meters with 40 number of blows at a grid spacing of 16 meters using a weight of 18.5, tamping enables a 10.96 meters depth of improvement. This is what the statement is. Like you are able to now design some in some sense using these two figures the depth of you are able to understand with a known weight and the height of drop, you will know what exactly are the variables involved. In fact, if you want to go for higher depth, you can increase the depth of height of fall. or if you want any other, you can always play with some of the variables and come out with whatever is required. Say for example, if you need only 6 meters, you can alter the whole design by using appropriately all the numbers, essentially, like the variables are that you will have height of drop is one variable, and the spacing is another variable. So, one can check and then come out with a simple design, and then once you have to, because as I just mentioned here, the design is a very like it is a very simplistic design, and the best thing is that you have to verify how it is correct, to what extent this deep compaction is effective. So, what you do is that we go for in situ evaluation of the deep compaction methods, and the way that we do is that you try to analyze the construction process itself, like to what, how is the process designed, like as I just mentioned, like the calculations procedures we have seen, we can do a parametric study on that and do a proper construction sequence. And then also, like say for example, if there is a problem of noise also with because of the deep compaction, you can even go for smaller heights and closer spacing, something like that. One can always work out some sort of processes wherein you can still get the effective improvement. And the other important thing is pore pressure and settlement records, because the pore pressures and settlements are very important. And say for example, finally you may have initial settlements very high, but the final settlements need to be very, very low, that is subjective. So, you can only get that from settlement records and pore pressure records. As I just mentioned, many of these materials like particularly in the process of dynamic compaction, the pore pressure is mobilized because the rate of loading is so much that there is lot of pore pressure generated, and the rate of dissipation of pore pressure gives you what type of soil it is. Like say for example, in clays you can only say that pore pressure mobilization is very important. So, you have to do the next time lag, you need to really next type of next tamping, when can you do, like you have done a few tampings now, how do you really release the next time the weight, some of these things you can get an idea from the pore pressures and settlements observations, and so that the things are effective. Like say for example, if you keep on tamping it without understanding its pore pressure response, it may not be very effective. But if you really understand all the pore pressures to be dissipated to some extent and then again tamp it, like your the sequence of tamping is something that can be properly optimized. Then what we do is that requirement of the imported fill to achieve a certain grade. Sometimes see what happens in a particular place, like the whole area is very soft, and or some, so you are bringing some other soil from nearby island, and then you are trying to see that it is densified, because in some places, for example, I just mentioned in Singapore and other places, you will see some more examples here, you have to get soil from somewhere and start compacting. So, in this process what happens, you have to really check if the imported soil has that properties, like if it has achieved that density or water content and all that. Then the another variable is that energy consumed by the equipment itself. Say for example, the energy that you have put into the soil system is something that has a very good influence. If higher is the energy that is transferred to the in situ system, then more efficient is the process of compaction. So, you must be able to analyze every bit of this information here and come out with proper understanding, and essentially if you want to really quantitatively and estimate the evaluation the state of the soil because of the deep compaction, you must go ahead with some tests. Say for example, you are familiar with SPT test, deep penetration methods, standard penetration resistance we should get, and the advantage is that you have correlations with the SPT and friction angle and relative density. Say for example, if the SPT value is 10 or 15, you can say what is the friction angle and then what is its relative density. Say for example, an SPT of 30 indicates a good relative density. So, like this, like if you have a SPT profile much before the compaction process is done, you will understand how much is the improved state of the soil. So, instead of the friction angle, say for example, in situ soil SPT could be 10, now if it is improved to 30, it is an excellent thing. now you also have cone penetration resistance, which is we call it CPT test, and here again we have correlations with cone resistance. Like here the cone continuously drives into the soil, and the advantage with the cone penetration is that it is a continuous record of the skin friction, shaft friction, pore pressure ratio and many other things. The advantage of the CPT is that it is continuous and it can record many measurements. In fact, it can even measure seismic wave velocity if you have a proper tip to the attachment to the cone. So, it is so much useful nowadays. So, here again you have correlations with cone resistance and overburden pressure. So, in fact, as higher is the overburden, higher is its resistance and higher is the relative density. So, you have some the literature available which will clearly tell you if the density is very good. Then the as I just mentioned, compressibility estimates from penetration tests. Say for example, if you, as I just mentioned, settlements are very important. So, if you want to measure settlements, you need to have proper instrumentation, and also you need to estimate settlements also. So, for example, you have an SPT value n, say 10. So, if you have if you want to use a modulus in any of the finite element calculations, so what happens is that you need to have these parameters in once for analysis. Once you do an SPT test or a CPT test, how do you use that in the analysis in design is very important. And suppose you have an SPT test, you can say that the Young's modulus is related to SPT value in this form, like E equal to 2.8 n MPa. It is a simple expression, and say SPT 10 will give you about 28 MPa, so which is somewhat poor, but then if you have a 30 number, it is quite good. So, again stress strain parameters from cone penetration test is another example. Constraint modulus is another value that one can get. You have different types of moduli in soils, like Young's modulus, secant modulus and many other parameters, like one dimensional modulus from constraint, the one dimensional consolidation test, modulus from triaxial test. So, one should understand them properly, and so you can have even as a simple relationship. If you know the cone penetration resistance QC value, it is a 2.5 times a QC is another expression. There is another equipment that we use in a very nice manner, which is called pressure meter test, in which you have a small tube which is which has a diaphragm, and once you insert it, it expands, and then you try to find out the both deformation and the pressure exerted to create that deformation. So, there are two types of equipment here. One is called Menard's pressure meter, and the other one is a self boring pressure meter. Actually, the Menard's pressure meter is a very standard one which was developed in France, which people have used extensively, and it has some parameters. You get Young's modulus, you get limit pressure. Limit pressure is related to bearing capacity of soils. Then we have called, actually we have to create a boring when you try to make a when you do a test using Menard's pressure meter, but later people have done a advancement that the pressure meter itself makes a self bore. It is like you make a bore and then put the instrument back. The problem is that there could be a sampling disturbance and other things. So, they have overcome some of these problems by using what is called self boring pressure meter, which is a very versatile equipment, and people have used it. There is here another equipment called dilatometer test. See, the pressure meter test and dilatometer test are very well practiced in like in Europe. For example, the pressure meter test is widely used in France, and then dilatometer test is widely used in Italy, because they are the countries of origin, but then they have found their places even in many other countries like US or even India. For example, pressure meter tests are done in NTPC projects, and many important projects people have been doing. Even say for example, the dilatometer test is it is a simple kit. They have a simple kit, and one can use that, like you here again the principle is that you just put that instrument in a particular borehole, and then you allow the diaphragm to expand, and the resistance to deformation is measured. The diaphragm starts expanding because you will be applying some sort of pressure. The pressure versus the deformation is recorded, and so you will get lot of information from both the tests, because the thing is that the advantage is that you do not need to take undisturbed samples, you are getting the response of the soil from undisturbed state itself. So, there is some more measurements on shear wave velocities which is very popular, we will see some of them now. Like say for example, this is a typical example, you can see that you have a ground surface here and then the water table is here, and you have a silty fine medium sand here, and it is about minus like it is there is a total depth of about 11 to 12 meters. So, the thing is that, so you need to really improve this, and then the problem is you have a groundwater table, that is very tricky. So, under these conditions it is not its dynamic compaction is quite effective. You can see here that before the dynamic compaction, the SPT values are like this, like they are in the range of 10. Once its dynamic compaction is done, you can see that they are in the range of 20. So, you can see that there is a good difference, and you see that in the case of a CPT, cone penetration test results, the QC is a variable here. You can see that the QC is somewhat in the range of 5 MPa, it just increases with depth, but then you have another QC gets improved with like this. Similarly, in the case of pressure meter test, it is called limit pressure. Limit pressure is another important variable in actually you will get a result from pressure meter using in terms of the limit pressure. You can see that the limit pressure is low when it is not improved, and when it is improved, there is a good difference. So, that is what I just mentioned. The pressure meter, this is a self boring pressure meter kit, like this is that particular material, and then this is a gauge, and this is a system, and then all of them these are the extension wise, you can go up to 10 to 20 30 meters quite comfortably, and you will get a nice profile of its properties. And a typical expansion here, you can just see that we call it cavity strain. Say for example, these things are all based on cavity expansion, like you add it's a there will be oil, and then you apply some pressure, it cavity expands, and then there is a strain here, cavity expansion strain you are trying to measure, and so this is how loading portion is there, and loading, and then this is unloading, it comes back. So, this will be the in a particular borehole, say for example, this is a old record somewhere which I took from some source. You can see that total pressure versus the cavity strain is given. This can be used to obtain various properties such as Young's modulus, bearing capacity, settlements, Poisson's ratio, many things. There are a lot of information on this. So, this is a dilatometer I just mentioned, a similar one which where you have a diaphragm here, and then it is a simple kit, actually it is a very simple equipment. This also has a very versatile applications, and shear wave velocity measurements. Here again, like as I just mentioned, whether the dilatometer is also very useful, pressure meter is also very useful, and shear wave velocity measurements. So, for example, in shear wave velocity, what do we measure? We measure the shear wave velocity, and actually since the shear wave velocities are measured from in a very using you just have an impulse created, and you also have a pickup. Say for example, here in this case, like you have an impulse here, then you have a rod here, you have a wedge, then it is picked up by a geophone, and then based on this you have shear modulus measurements, Young's modulus measurements, and all that. So, you can see the difference here, like before dynamic compaction, the E values, the shear wave velocity values are like this, whereas after deep compaction it can be like this. So, what I mean is that some of these in situ techniques are very essential, particularly right from SPT value, cone penetration, pressure meter, then flat dilatometer and shear wave velocity measurements have been very effective in improving the in assessing the improved state of the ground. So, what I will do is that I will just take you to a few case studies because this is, say we have some case studies which are well documented. You can see that this is a nice airport runway, new runway. In this case, an extension was made for the existing nice airport by constructing 2 new runways. The runway length is about 3.2 kilometers long, parallel to the shoreline on a reclaimed land. Actually, the reclaimed land is something that has a very low properties, low, like the soil conditions for loose fill, some stiff marls and deposits of soft sandy soils, and hence there was a need for heavy dynamic compaction inner and around the, close to the runway. This is the problem, and so what they did was that they had to place about 20 million meter cube. Quantity is so high, 20 million meter cube of fill to build a reclaimed platform of 200 hectares. Area you can see, imagine that area 200 hectares is quite high. The borrow pit was situated at a distance of 13 kilometers from the main site. The transport was made by means of a fleet of about 38 dumper trucks. The number of trucks that are going from over the distance of 13 kilometers are about 38, and they have a trailer weight of 145 tons. The weight that they can carry. You must be able to design your even your the transportation system also very well in a ground improvement project, because you can't you have to get as much as material as possible, so that you can start reclaiming and then doing the compaction and then recover the soil faster. So this is a big process involved in this planning of operations for dynamic compaction. So in this case, the evaluation of pore pressure was continuously monitored at various depths during the dynamic compaction. As I just mentioned, the pore pressure variations during dynamic compaction have a very significant role on trying to decide about the construction, the tamping operations, the release of load and all that. So the work in this case was done in phases with sufficient resting periods to avoid building up of excess pore pressure. The volume versus DC or the dynamic compaction energy governed the intensity of the treatment. So for example, how much is the volume that has been compacted, and the energy input into the system is something that is very important, and they were able to understand this process. And during the dynamic compaction after the treatment, they have done number of CPT tests, pressure meter tests to control the fill characteristics. You can see that this is the process of compacting, like you can just see that they have a specific sequence here. So there is another example here where for a desalination plant in Saudi Arabia. Actually, this is one of the plants which required which was required to be constructed to meet the growing demands of the water and electricity in Saudi Arabia, in some close to about 110 kilometers from Jeddah. And the soil has 2 types of profiles, and this first one was the loose material, loose to dense sand, and the second profile was composed of soft or a very loose silty sand. This was followed by bedrock. So you can see that it is quite complex, and so what they did, like it has the projects also had, it's quite huge, like since it's a more of a water supply project, it had 12 evaporators, 3 tanks and number of related buildings. The tankers diameter and height were about 106 meters and 20 meters high. The design criteria stipulated a bearing capacity and maximum settlement of about 200 kPa and settlement of 75 mm for the tanks. See, this is even we have, for example, in very soft soils, on soft soils you must be able to construct water tanks in villages. So for example, in many of the coastal areas in India. So the bearing capacity requirement could be like this, and the settlements could be even this 75 mm is valid there also. So you need to really improve the particular thing using particular some sort of ground improvement technique. So, that way one can see that this is a very stringent requirement. You can see that for the water tanks they had a 200 kPa as the bearing capacity and 75 mm is the settlement. For other structures the same was required to be 150 kPa and 25 mm set respectively, like 70 mm is it all of structures. Say for example, the water tanks, it could be little higher, it may be a raft type of foundation that they had, but in this case of isolated footings you should have a settlement of 125 mm or something. So, it is very important that the whole area needs to be stabilized. So, because there was presence of loose sands and soft silts, it was decided to optimize the foundation solution by implementing dynamic compaction and dynamic replacement in the project. So, the choice of this technique was dependent on the soil characteristics. You can see that upon completion of the soil improvement work, this is the type of work that they have undertaken. This is from the particular company. They have done 75 pressure meter tests and load tests to demonstrate that the acceptance criteria had been achieved. Say for example, the acceptance criteria is what? The bearing pressure and settlement. So, you can calculate the bearing pressure settlement using limit. You get a parameter called limit pressure. Limit pressure is related to bearing capacity from pressure meter test, and also settlements could also be calculated. So, the acceptance criteria of settlements and bearing capacity is met using this. So, the results clearly showed that the success of the ground project and the ability of the foundation to safely support the design loads. So, essentially you must be able to give guarantee for whatever you do. Say for example, the soil is so soft, you must be able to improve to the required capacity whatever the client asks. So, that is a very important thing here, and you can see that it is a square plate that what we use in our design, roughly square. Okay. There is another one which is an airport that close to a road actually. It is widened up to 200 meters by reclamation of about it is about 0.9 million square meters actually. It is for using dredged sand for a depth varying from 4 to 12 meters, like the road widening project, so it has to, it is a lot of filling is involved. So, they got the sand from some places and then they filled up to 4 to 12 meters, and the length of the structure is about 4.75 kilometers, and actually it should have been anchored with sheet pile walls, but it could not be embedded into hard rock, and it was necessary to be equilibrated by a well compacted submarine backfill to generate necessary horizontal reaction. Actually, in the sheet pile wall construction, the thing is that you also need, if you have a well compacted backfill as a behind the sheet piles, the earth pressures coming onto the retaining wall are much less, like you can optimize the design in a proper way. So, for example, you have a sheet pile wall, you have a less good backfill that is next to the sheet pile wall, definitely the load that that comes on the sheet pile wall will be much lesser compared to what it can be in the case of a poor soil. So, what they did was that they used a dynamic compaction with a 15-ton pounder and a high energy dynamic compaction. You have two types was done for the main part of the fill with special emphasis on areas with sockets. So, you can see that next to the sea beach this is all done, and near the sea beach, like with a denser grid on an initial enlarged area, and a platform was constructed, later excavated after soil improvement completion was done to achieve the final shape. So, measurements were done with pressure meter test and finite element calculations. In fact, one should verify some of these calculations and prove that, and because you need parameters like Young's modulus and other Poisson's ratio and other model parameters for finite elements, one should use sophisticated testing. That is the reason, in fact, pressure meter test was used. So, what I would like to say is that of course, I must thank some of the sources from which I got this particular equipment, like particularly Hayward Baker and Menard, this thing, and Hausmann is a book I followed. What I want to say is that we are able to in this particular section, we are able to understand what exactly are the issues that are involved with dynamic compaction, and we have seen how what are the different types of dynamic compaction involved. Say for example, dynamic consolidation is one variable. We have seen actually whole of the Shanghai airport was constructed because of that, and there are some more case studies that we have seen, and so this technique we are able to see the design, like we have used a simple method in which you can design based on the weight of the weight available. You can design the height of drop and the spacing, and for the required depth of improvement. Actually the depth of requirement required depends on, say for example, you say that 2B is a significant zone. Say for example, you have a footing B, 2B is a significant the depth of pressure bulb. So one must be able to calculate the significant zone. Say for example, using even finite element calculations, you can simulate the whole structure at the top of the soil and then understand where the stresses are coming. Say for example, if the stresses are going to reach to a very soft area, then the problem is that it could lead to lot of settlements, and one should really optimize and then see that those settlements are not there. And then so these are all some of the issues that one needs to understand and see that dynamic compaction is done in a proper way. And there have been many case studies even in India also, where particularly in many of the coastal areas the dynamic compaction was done, in flash ponds it was done. So it has been quite effective because the method itself is quite simple, like it only involves the weight to be dropped for a to a pre everything is pre-designed, and say for example the height and the spacing and all, and the only problem is to what extent you are correct, is the improved ground okay. So that can be only ensured by proper in situ testing using SPT or a cone penetration or pressure meter tests. Once it is done, it is ready for further construction. We will take up one more case study on dynamic compaction. This is a case study from India, where it is for a fertilizer plant at Babrala, UP. The ground improvement technique using dynamic compaction was required. In this area, you have a surface layer of silty sandy clay of about 1 to 2 meters, and beneath that you have a loose fine sand of about 10 to 12 meters, and again a silty clay. The parameters available at the site before treatment indicate that the allowable net bearing capacity was about 60 kPa, whatever is the allowable bearing pressure is about 60 kPa, and the other design requirement was that for this fertilizer plant, people have done seismic risk analysis, and they find that the design earthquake coefficient should be corresponding to an earthquake of magnitude of 6.4, which is corresponding to peak acceleration of about 0.2 g. So what they observed was that if you have this sort of acceleration that is coming in the site, then since the material is of loose sandy type, there is a possibility of significant liquefaction, and they do not want that. So they wanted to essentially go for a ground improvement technique, which has been essentially using dynamic compaction. These are all the areas that they have identified in the site. It has a big area which has been marked here, A, B, C, E, D, all that. And first thing what they did was that trial was done in areas of 30 by 30 meters using dynamic compaction, because it is very important to just do a trial test in dynamic in dynamic compaction, or even for that matter in any ground improvement technique, because you will exactly understand how is it working in the field, and you can fine tune it also. Like if you are not really doing well, or if the assumptions whatever you made are not appropriate, then you can really make some corrections in the design. You can see that this is the experiment that was done on the field, trial site, where they did static cone penetration, both SPT as well as standard penetration as well as static cone penetration test, and this is the figure that shows the profiles. You can see that the SPT profile is very clear, like the SPT value is very low, like 5 blows, and then whereas it increases about 15, which is not really a good number. I mean, so of course we know the trend that the strength increases with depth, but even the value of 5 to 10 is quite low. Now after the improvement, they just see that they made it, they did some sort of testing in it, it's a trial section. You can see that the SPT improved to some extent, and it was good everywhere. This point was away from this point, and there is a good difference. And one can also see that there is another line, that if you take SPT values after 1 month, there is another increase, some more increase. What it means is that normally like in the time dependent behavior is that if you allow things to happen, like say for example consolidation is a time dependent phenomenon in clays, even in sands also, like because of the pore pressure dissipation in about 15 days to 1 month time, there was an increase in strength which was observed, which is good. So based on the results from the trials, modifications were introduced to obtain the allowable bearing pressure of 200 kPa at 2 meters depth. This is what they wanted. So for example, this is the allowable bearing pressure 200 kPa 2 meters depth, and the other thing was that no liquefaction should occur in the improved ground during the earthquake. Actually the requirement is that, in fact there is a standard rule, like if the SPT value is about 25, then the liquefaction will not occur, which means that there is a very good density. So there are some criteria one needs to fix up in the particular site, and so that, say for example, we know that we know how to conduct an SPT test, we know how to correct all the they have so many corrections in the SPT test. So one should get the correct number, like a design SPT value, and then correct it using for the energy, energy like 0.65 or the 65% efficiency and all that. And there is a criteria that whatever like you should be able to get the number, what should be the actual field number that should be there, that you should achieve with your equipment, one should be able to get. Say for example, if it is 25 as a SPT value, then everywhere all along the profile the SPT value should be more than 25 or 20, whatever. So in this case, once they really figured out that these are the requirements in the particular site, they went ahead with the treatment, and it is very interesting that they had 4 passes. It is not number of passes like 4 tampings. The first pass was with a 10-ton hammer falling 16 meters. The second pass was similar, but the locations were staggered, like they just put a little bit of staggering there. And then third pass is with a 15-ton hammer falling 16 meters. Now the weight of the tons is like it's a little higher, like 15 tons. In the previous case it was 10 tons. And finally in the last one it was made with a 5-ton hammer falling 16 meters on a grid of 2.5 into 2.5. Actually in the beginning itself I just said, if you just make it closer, then you have a shallow depths densified. If you take little deeper, the possibility is that the deeper materials get strengthened. So these concepts one can use and then come out with some good improvement. You can see that the treated soil was was assessed in terms of the SPT values, because that is a assurance, like if the contractor does that work, you have to see that you get this number. So the quality assurance program consisted of having SPT values more than what is required. So for example, you can see that this is the before, it was like this, but whereas it was consistently about 20, say for example it is 20, which is reasonable. So this is in a particular location, area A. Then in the other location, area B, you can see that it's always more than 20 everywhere. You can just say that one point it's touching. Here you can see that in the area C, like there is some one point which is somewhat less than 20, but all other points are okay. So actually sometimes this also, like the earlier the specification was that at the top 2 meters there should be a good bearing capacity. Okay, this could be an aberration actually, because the possibility is that this when there is a good value here, there is a good value here, possibly this number could be wrong. So one should really take like that and then come out to say that yes, this SPT value criteria is satisfactory. So this was what the people normally say, and in this case definitely the dynamic compaction was very successful in significantly increasing the strength of the soil, and this translates to a more than threefold increase in bearing capacity, like what we thought was 60 kPa, now we got 200 kPa. So that was quite good. Then the soils were treated to loose sands up to a depth of about 12.5 meters, and bearing capacity is increased to whatever we wanted, and also the earthquake resistant design was possible. That was what I meant, and particularly these people have explored lot of other options in the site, like any other similar treatments, like removing the whole soil, trying to backfill, and some of them like trying to do the piling. So for example, if you want to increase the bearing capacity of the foundation area, like why don't you go for piles, why do you go for just simply compaction, which we do not know much. So some people like it depends on the consultant that the project has. If somebody is a geotechnical consultant, he will be able to give geotechnical alternatives, but if there is a structural consultant, maybe he may recommend piles because he has lot of confidence. So in this case the technique was very effective and cost effective. In fact it is very maybe 40% cheaper or even 50-60%, because piles are expensive, and definitely when you do the compared to just a tamping that you are trying to use and do SPT test and all that, definitely what we are trying to do is that we are trying to improve the soil as it is, rather than trying to remove the soil and then put with an RCC and put some piles and all that, which is not which is efficient in terms of the efficiency. Definitely you should improve whatever is existing, then that may be always cheaper than trying to replace the whole material or try to ignore that material, like soil strength. You ignore the soil strength actually in many of these cases. You do not particularly when you design the pile foundation, you do not consider the soil between the two pile groups, or what is the role. Maybe you can consider the skin friction and something like that in a sandy material, but its contribution largely is ignored. But then here in the ground improvement techniques, what we do is that we just compact the material to what we want, like then some performance you specify, say for example SPT 20, you will get it. You have to do it till you get it. So particularly this is very useful when you are trying to handle large foundation areas, say for example coastal areas. They result in cost effective solutions, because depending on the size of the project, the type of soil conditions, say for example as I just mentioned, the techniques of dynamic compaction, the range is quite big, like right from municipal solid waste to sands it can take care, and the cost of suitable fill material is also important. Like in some places you have to borrow some material, like say for example we just now in the previous case studies we saw that in some places to construct the airport you should bring soil from nearby islands. So possibility is that they could be expensive. So one should really weigh against many alternatives and decide about which is the best. So in this lecture I would like to thank many of these people, Shafra Jali, Professor Gandhi, and then some material I have taken from this and Hassman book. So I am sure that with this you have a good understanding of the ground improvement technique using dynamic compaction.